Hello, everybody. Before we start on continuing sugar chemistry, let's do a problem that's building on what we learned during the last two lectures, namely the oxoester type synthesis, also called the acetoacetic ester synthesis, using this unit, cheap available starting material, to construct something more complex. And so when we look at the product here, and of course the starting material, remember that the starting material is really a way to get around fighting the basicity of an enolate anion. In this particular case, this is equivalent to, once you make the anion, to acetone enolate, okay? Acetone enolate alkylation is terrible because of E2 complications. This one, we can alkylate, this anion here, we can alkylate readily because it's a highly stabilized negative charge. It's much less basic, okay? So you can alkylate with anything you want, of course, except with tertiary. Tertiary systems always eliminate, okay? So we use this unit that is made, as you may remember, by the Claisen condensation of the corresponding methyl acetate. And bearing this in mind, and then looking at the product, you recognize that we should look for strategic disconnections that deal with making bonds to acetone, okay? And the acetone unit that is tractable is this one here. So retrosynthetically, bearing in mind that we're going to use this would be the disconnection. Alkylation with two different pieces, quite straightforward, really, once you think about it. So you need to understand what's going on, and then everything becomes very simple. To a methyl using as the alkylating agent methyl iodide, or any methylating agent that you have, that you remember, methyl chloride, methyl bromate, methyl sulfate, whatever. That introduces this methyl group, and then we have an unusual alkylation at this position here. And here you should remember that this is the beta carbon of a carbonyl compound, and these can be accessed by using conjugate addition chemistry. Okay? So this is a Michael addition, enolate chemistry, to this carbon here. So these are the two alkylating agents that we need to use to pull this off. And after that, things get quite simple, so we can do this now in a forward sense. Starting with our starting material, we make the amine in methoxide methanol, since this is a methyl ester. Remember that this is used as two equivalents. Well, we can use it as the methoxide to make the anion first. And remember that this reaction is exothermic to the right, so the equilibrium here between starting material and enolate is way on the right, okay? Because the pKa of this is way below the pKa of methanol. In fact, it's about 4 pK units, so this is about 10,000 to the right, if you're thinking of this as an equilibrium. This is very much unlike treating acetone with hydroxide or methoxide. There, the equilibrium is way to the left, okay? So you use up a stoichiometric amount of methoxide. This is not catalytic, so maybe the way to put this is one equivalent. And this now is capable of alkylation, so let's do the methylation first. And that introduces the methyl group. And then we treat it again with methoxide, one equivalent, in methanol, which pulls off the second proton to make another anion, now the methylated anion. And this is then treated with cyclohexenone, because this is the Michael addition of this enolate onto the beta carbon of cyclohexenone, and the job is almost done. So we now have introduced the two alkyl groups, and this connection here is at the beta position of this carbonyl. And then we hydrolyze and at the same time decarboxylate to get rid of the enabling ester function. So it's purely, this ester function is purely an auxiliary that allows you to make an anion that looks like this one, but it's not as vicious. Okay? And that's probably best to do this with acid, H2O, and heat, because under these conditions you get directly the carboxylic acid and it will lose carbon dioxide. And that's the product. So with a lot of these reactions now, you probably are pretty good now at reaction chemistry. Part of the trick is to recognize the simplest patterns. And again, as usual, there are frequently different solutions to a problem. This one is highly restricted because I'm asking you to use this specifically as a starting material. But if you didn't remember this Michael addition scheme here, you could still work your way around it in a more long-winded synthesis by getting rid of the carbon dioxide at that stage and then trying to build up this unit in some other way. And there are many, many ways of doing that. So you could try and doodle at home trying to see whether you can make this thing, the product, in a different way. Okay, so we started to talk about sugars. And we noticed that the simplest sugars are so-called monosaccharides. They're just single molecules. They can contain 3, 4, 5, 6 carbons in a chain. Beyond that, nature doesn't really bother much. There are some larger ones, but you mainly stop at 6. And the trick is that they contain one carbonyl function. And the way we depict them is using Fischer projections, the Fischer stencil. And we always put the carbonyl furthest to the top. So there can be aldehydes, in which case they're called aldoses. And the 4-male function, the carbonyl is at the very top. Or there can be ketones, which are called ketoses. Then the carbonyl is one down. Okay? And then after that, it's always HOH, left and right, or right and left, depending on the stereochemistry around this particular carbon. And it's not really necessary to identify what the stereocenters are, ROS. You can try and do that for a couple, just for the fun of it, but that's not the issue. The issue is, the relative stereochemistry, where do these hydroxy functions sit in terms of bookkeeping using our Fischer projection. If you were to convert the Fischer projection to a zigzag line structure, then you get a beast like this. This is glucose, where we have the aldehydes. The way I'm lining it up now, the aldehyde is to the right, so here's the CO double bond, and there's the single hydrogen, and then it's HOH, 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 and at the very end you have CH2OH. And if you were to turn this into a ketose, the isomeric ketose, which is fructose, then this carbon would be the CO double bond, and that guy would be CH2OH. Okay? So these two hydrogens basically transfer from this carbon over to there, formally, topologically, not chemically. Okay? That's a difficult thing to do, although that's possible, actually. So you can see that the zigzag notation actually is not readily recognizable in the Fischer projection. The reason for that is that the Fischer projection is an artificial construct in a way. It's the old staggered arrangement, okay? So that each carbon, where there's the cross, right, the rest of the stuff goes to the back and the two horizontals come towards you. And you can see that if you were to translate a Fischer projection into a molecular model and leave everything the way it's depicted in the Fischer projection, then you would get an all eclipsed chain. Okay? Everything would be eclipsed, and this thing would sort of fold around itself to the back. An impossible structure, actually, okay? Because things want to be staggered, as shown here, and they wanted to set up the zigzag arrangement. So it actually takes quite a bit of acrobatics to do this on a piece of paper, and I'm not going to do that to you. Okay? So there's an attempt of this in the book, starting with this slide here, but we won't do that in an example, and it's not really necessary. So having recognized that we're dealing with polyhydroxy aldehydes or ketones, you probably already realized that there is an alternative form of these kinds of molecules that is based on the fact that they are hydroxycarbonyl compounds. And if you go back and remember chapter 17, when we dealt with hydroxycarbonyl compounds, we had a few of those, we realized that the hydroxy function further down the line, away from the carbonyl, can come around and form a cyclic hemiacetal. And in general, hemiacetal formation from two molecules, one aldehyde or ketone and one alcohol, already was not particularly favored. In the case of aldehydes, which are fairly reactive carbonyl compounds, the equilibrium ratio was about 1:1, starting materials and hemiacetal. That is the adduct of the alcohol to the carbonyl. For intramolecular hemiacetal formation, because that is less entropically costly, it's actually a little better. The equilibrium lies to the right, noticeably. Okay? And this is exactly the scenario we're encountering in the sugars. We have a hydroxyaldehyde or ketone where the hydroxy function, one of them, or several, can swing around and add to the carbonyl molecule. And so if we try to do this on a piece of paper, you start with the zigzag notation of the, in this case, glucose as an example. That's exactly the structure I have here sitting in front of you. And you have to decide which ones of these hydroxys should add to the carbonyl to form the cyclic hemiacetal. And in principle, all of them are capable of doing that. So if you start with the one right next to the aldehyde, that OH can swing around and attack the carbonyl carbon. The proton transfers to the carbonyl oxygen, and you have a cyclic hemiacetal. But if you look at the structure that you get, it's 1, 2, 3 atoms. It's a 3-membered ring. And that's terrible. Okay? So this may happen kinetically, it may add, but it immediately swings back because this is not a particularly thermodynamically favorable situation. So we can go to the next one. That one would make a 4-membered ring. That's not good either. Okay? So it only becomes feasible when at carbon 4, when this OH potentially swings around, that would make a 5-membered ring, or this OH swings around, that would make a 6-membered ring. And indeed, 5 and 6-membered rings, I've been drumming this into you repeatedly in the reversible reactions. Those are the ones that are the final outcome of these intermolecular type cyclization reactions. So if you translate this structure then therefore to one in which the chain loops around so that these OHs get close to this aldehyde, we have two options. One is the OH at C5, if that adds to carbon 1, and so this is indicated specifically here, OH is the nucleophile, the proton gives over this oxygen, we get this beast here, which is sort of indicated in the 6-membered ring structure, desperately trying to keep track of where all the other OHs are. Okay? The important point, however, is that adding to that carbon turns the sp2 hybridized carbonyl carbon into an sp3 hybridized carbon, which is a new stereocenter. And there's a possibility, therefore, of making making ROS at the center, meaning that you get two new diastereomers, where, formally speaking, the OH can be down, cis to this neighboring OH, for example, or it can be up, trans to this neighboring OH. This carbon is an acetal or hemiacetal carbon. Okay? It's a labile carbon because this is reversible. Okay? And it just so happens, since this is intramolecular, the equilibrium lies on the side of the cyclic hemiacetal. But there are two isomers of this cyclic hemiacetal. 6-membered ring formation, because it's an oxocyclohexane that bears some resemblance to this heterocycle called pyrane. These guys are therefore called pyranoses. When you make a 6-membered ring hemiacetal, it's called a pyranose. You don't have to remember that, but I'm telling you. Those of you who are going into bio, you'll get heavy dose of sugar chemistry potentially, maybe even going to a lab. Since this is a very hot research area in bio, you will have to review that and remember, pyranose is the 6-membered ring formation. And that's the most stable of the two diastereomers around this so-called anomeric center. So because this is a special sugar hemiacetal carbon, people felt compelled to give it a separate name. The anomeric carbon and the two diastereomers, OH down versus OH up, they're called anomers. Okay? Extremely annoying, of course, because it's completely unnecessary, but that's what has been done. We'll just talk about the two diastereomers at the hemiacetal carbon. Okay? So this is reversible. Then there's an alternative way of cyclizing, namely taking the OH that's sitting on C4. When you swing that around and add to the aldehyde carbon, you get a 5-membered ring. Cyclic hemiacetal. Again, a new stereocenter. Again, two diastereomers called anomers, and this guy's called the anomeric carbon. Again, OH can be up or it can be down. Okay? And the 5-membered ring, perhaps predictably, is the less stable of the two. 6-membered rings are, in cyclohexane, they're called strainless, right? And if you remember chapter 4, look this up, 5-membered ring still had a couple of kcals of ring strain. 6-membered ring, cyclohexane, in a chair configuration was strainless. Okay? So that's why this is slightly less stable. So it's there in this mixture in 0.4%, and this guy's there 99.6%. And it's in equilibrium with the acyclic form. And so looking at adding up these numbers, this comes up to about 100%. Indeed, that's the case. This guy is there in 0.003 3%, something like that. I think we'll see that number in a minute. So it's a minuscule concentration of the glucose that we typically write like that, or using the Fischer stencil. It's a minuscule concentration in solution of this stuff. If you were to take an NMR, all you would really see is this. Okay? 0.4% is already difficult to see by NMR. You'd have to blow up the spectrum quite a bit, and 0.00 whatever percent of this is almost impossible to see. So the aldehyde that's typical of the open chain form, which is a typical signal way to the left in your NMR spectrum at around 10, way out of the range of everything else, you couldn't see it, because the compound isn't there, so to speak. It's traces only. But there's a rapid equilibrium that equilibrates all of these three guys. So when you talk about glucose, that's fine, you can write a structure, but as soon as you put the stuff into solution, it's actually a mixture of three compounds. Well, more than that, it's actually a mixture of five compounds. The open chain compound, the two diastereomers of the furanose, and the two of the pyranose. And I forgot to mention, these are called furanoses because this five-membered ring is related to furan, which is a heterocycle we'll deal with next chapter. But you've seen tetrahydrofuran as a popular ether solvent. That's the tetrahydro derivative of furan. So the common name is furanose. Okay? And so this would be, as it's derived from D-glucose, and we're only dealing with the D isomers of all the sugars because they are more related to nature. Certainly for glucose, this would be D-glucofuranose, and this is D-glucopyranose. Okay? So if we look at that molecular model of this, and I advise you to make a molecular model so you can see this very nicely. Of all the hydrogens that can cyclize, the best ones are this one and that one that swing around to add to this carbonyl function here. So this guy here will give you the six-membered ring, the most favored. Okay? And you can see that as I'm getting closer with this OH in my right hand to the carbonyl in my left hand, the chain starts rotating, things start rotating around and so forth, adopting a configuration that ultimately is sort of pseudo chair. And my right hand then approaches my left hand to attack this carbonyl carbon nucleophilically. Okay? And if you think this through, there are two ways of attacking. This way, where I have the carbonyl oxygen in my left hand is pointing up, or that way. And that's the origin of the two diastereomers. If it attacks here, you get one diastereomer. Attacking here, you get the other diastereomer. And the most stable one, in the end, is this guy, which you may or may not see how this, when it makes a bond here, that's this bond here. Let me hold it up. And you get the six-membered ring, cyclohexane chair type compound. One of the carbons is an oxygen. Okay? And the hemiacetal carbon is right this one. Okay? So this used to be the CO double bond. This used to be an OH, and it's added to here. And one thing that you may already actually see, it's quite startling actually every time you make this model, how beautiful this is, to me anyway. You notice that the most stable compound that we saw on the top right, the beta, so-called beta diastereomer, is all equatorial. All substituents on the six-membered rings wind up in the equatorial positions. In other words, that is indeed, just based on conformational arrangement, the most stable configuration that you can write for an aldohexose cyclic hemiacetal. It's glucose. It's the stereochemistry sequence in glucose that allows you to make an all-equatorial cyclic hemiacetal. And this is why nature picked it. Nature isn't stupid. Nature figured that this is the most stable arrangement. That's the sugar I want to use to do a lot of chemistry with. And indeed, glucose features tremendously as the unit that is used by nature in a bunch of compounds. By far, 99.99% of natural saccharides are based on glucose. And you get a feeling for this by recognizing that, for example, starch, all the starch in rice, potatoes, bread, and is a polymer of glucose, okay? Where you're linking, and we'll see a picture of that at the end of this chapter. You're linking glucose by ether linkages such that you get a polymer. And cellulose is an isomer of starch, where the linkage, the stereochemistry of the linkage is inverted at one center. But otherwise, it's exactly the same. It's glucose, all glucose polymeric structures. Yeah, that was a question.
Does the stability of glucose in the chair conformation where it's all equatorial, does that contribute to the equilibrium of the hemiacetal formation?
Yes, that's the fact that, if I reinterpret this, the fact that you can form the all equatorial form contribute. Yes, absolutely. That's the origin of the stability, the relative stability of these two diastereomers, OH up versus OH down. It's the OH up, the so-called beta isomer. When it's up, it's called beta. When it's down, it's alpha. That gives you all equatorial. So the other diastereomer, so there's a second diastereomer to this structure here, which is the less stable one, where the OH is down rather than up. So the OH can be either equatorial, that's the most stable diastereomer, or it can be axial. But in all the other sugars, these stereocenters, which are part of the HOH going down the Fischer projection, when you invert one, it means that one of these guys is forced to be axial. Okay? So all the other sugars in the aldohexoses are therefore less stable in the cyclic hemiacetal scenario. So you can do the same thing with fructose, except that now, so yes, I spliced this in last night to give you the Fischer-type projection of fructose. Now it's an isomer of glucose, but the carbonyl is now a carbon 2, and therefore the top carbon is CH2OH. And so therefore now, in order to make a 5 or 6-membered ring, for the 6-membered ring you now take the terminal OH and swing around, and for the 5-membered ring you take this OH and swing around. So you start with the zigzag notation, and then you come around, say, with this OH and add to the carbonyl as shown in this structure here. So it's carbon 6 OH adds, then you get the 6-membered cyclic hemiacetal of fructose. Notice that things are a little different now because you're adding to an internal carbonyl, so instead of having a hydrogen now at the hemiacetal carbon, it's CH2OH. Okay? But otherwise, the same scenario holds. OH can either be down or it can be up. So you get two diastereomers of this compound. So it's a diastereomer mixture of these two materials. And